I recently came across an article by Daniel Cleary that was published in the journal Science that described an X-ray telescope that the Japan Aerospace Exploration Agency plans to launch into space on August 26, 2023. This video is based in part on Cleary's article. It turns out that this is the fourth time that the JAEA has attempted to put this type of instrument into orbit. The first one did not go into orbit, the second one reached orbit but stopped working shortly thereafter, and the third one reached orbit and worked for 5 weeks before the spacecraft carrying the telescope broke apart. If this X-ray telescope can be launched successfully into orbit, it will open a new window into the universe. Conventional telescopes look at photons, tiny packets of electromagnetic radiation that are mainly in the visible part of the electromagnetic spectrum. Stars emit copious amounts of electromagnetic energy, or photons, with wavelengths that are in this visible part of the spectrum. Astronomers use instruments attached to their telescopes called spectrometers to identify sharp lines, actually very narrow bands, in the visible light captured by their telescopes. It turns out that these sharp lines correspond to photons with very specific frequencies that are emitted when excited atoms of a chemical element jump from higher quantum energy levels to lower energy levels. By identifying these lines, astronomers can determine the chemical makeup of the star or other object that they are viewing. The first spectrometers for analyzing visible light were based on simple prisms that you probably are familiar with. Now astronomers have much more sophisticated spectrometers that allow them to readily identify the chemical elements producing the light captured by their optical telescopes. While stars emit copious amount of visible light, there are many astronomical objects of interest that emit electromagnetic radiation that's outside the visible range. For example, the hot gases that surround supernovas and black holes, and that also are found in galaxy clusters, emit very, very energetic photons with frequencies that correspond to X-rays rather than frequencies corresponding to visible light. These X-rays are so energetic that they can break apart or ionize the molecules of gas that make up our atmosphere. As a result, X-rays coming into the Earth's atmosphere are absorbed well before they can reach the surface of the Earth. Thus, astronomers who want to study these X-rays are forced to use instruments carried in orbiting satellites. As an aside, the relatively short range of X-rays in air, while a problem for astronomers, is beneficial for animal and plant life here on Earth since it shields it from the harmful effects of X-ray radiation. At present, X-ray astronomers are dependent mainly on 2 orbiting satellites carrying instruments to detect X-rays. Both of these satellites are more than 20 years old, and they don't have the capability to measure the frequencies of the X-ray photons that they detect. The XRISM satellite that will be sent into orbit by the Japanese makes use of a spectrometer based on a device called a micro-calorimeter, which was developed by NASA engineers in the 1990s. This device can measure the energy of individual X-ray photons that strike it, and the frequency associated with the X-ray photon then can be obtained directly from its energy by dividing by a number known as Planck's constant. In order to measure the energies of the individual X-ray photons, the micro-calorimeter must be cooled to very near absolute zero temperature. The XRISM satellite uses liquid helium to cool its micro-calorimeter to this very low temperature. It will carry enough liquid helium to last for about 3 years. In addition, the satellite also will carry a mechanical refrigeration device that should allow it to collect useful data long after the liquid helium runs out. With its ability to determine the precise energy of the X-rays radiated by interstellar gas clouds, astronomers can determine the chemical elements in the supernovas that emitted these gases. In addition, if they observe broadening of the sharp lines associated with specific gas elements, they can get a good estimate of the velocity of the individual gas molecules emitting the X-ray photons. This will allow astronomers to estimate how rapidly the gases in these clouds are moving. Based on the results that the X-ray astronomers obtained during the short time that the third Japanese satellite was in orbit before breaking up, they expect to obtain a host of new information from XRISM. Let's hope the launch of the XRISM satellite is successful and that it provides the X-ray astronomers with data for many years to come.